In this video, we'll begin our journey into tree-based methods for supervised learning tests. We'll focus on using trees for classification, but trees are also quite useful for regression tests. You very likely encounter decision trees in some form before, in flowcharts or infographics. Take, for example, the snippet of a decision tree to help you decide what video game you should play next. The use of a decision tree is fairly intuitive. We start at the top of the tree and follow the paths corresponding to answers to the questions posed in the rectangles. Ultimately, the final node we reach is our game recommendation. In the use of this decision tree, we can think of the cases in the dataset as people, the questions and rectangles as predictors, and the final nodes as gaming personalities or class labels of some sort. In general, the strategy that decision trees make for making predictions is to continuously split the data based on the predictor values until good predictions are reached. Let's look at an example of a heart disease dataset available with the ISLR book. The response variable we wish to predict is whether a patient has heart disease. We wish to predict heart disease from other clinical characteristics. The bar plot at the bottom shows how the probability of having heart disease changes based on the outcome of a thallium stress test. We see that a normal result on the thallium stress test is associated with a much lower chance of heart disease than a fixed or reversible result on the test. We might imagine that splitting the data into those with normal and non-normal results is sensible for predicting heart disease. A decision tree using just this variable is probably too simplistic, but let's look at the resulting tree just for illustration. Each junction in the tree corresponds to a statement about a predictor that can be described as splitting the data into subsets. We see that the thallium stress test predictor is considered, and the data is split based on whether the result is normal or not. If yes, then we follow the branch to the left. If no, we follow to the right. Each rounded rectangle is called a node, and the nodes at the very end are called leaves. Each node has 3 lines of text. The first line is the predicted class at that point in the tree. The second line is the predicted probability of the y=1 event at that node. The last line is the percent of the data that are present at this node. The topmost node, also called the root node, summarizes the data before any splitting, which is why 100% of the data are present at this node. The predicted class is no heart disease because the majority of the cases, 160 out of 297, don't have heart disease. Following the split to the left, 55% of the cases have a normal value on the thallium stress test, which is why the leftmost leaf has a 55%. Correspondingly, the right leaf has 45% of the data. So 55% of the cases move to the left on the tree, and among these cases who have a normal stress test result, only 23% have heart disease. 45% of the cases move right on the tree, and of these cases with a non-normal test result, 75% have heart disease. A full tree grown from all predictors is shown here. Let's notice a few things. First, although it's only labeled for the first split, we always go left when the condition at the branching point is true, and we go right if the condition is false. Second, a predictor can be used multiple times in the tree. The calcium and chest pain variables are both used twice in the tree. This just means that once the data were split in a particular way, these variables ended up being useful splitting criteria again. Note that for quantitative variables like calcium levels, the split is determined by being above or below a single threshold. For chest pain, if the chest pain variable is one of the non-anginal, non-typical, or typical categories, the condition evaluates to true. Third, notice that when we follow a split to the left and right, the predicted probabilities for predictions of no heart disease get closer to 0, and the predicted probabilities for heart disease get closer to 1. This is actually desirable because as we go down the tree, we want our splits to make us more and more sure of our classifications. The probabilities of heart disease getting closer to 0 and 1 reflect that most of the cases in these leaves are of one class label only. As we'll see next, this is related to the idea of node purity. and the process by which these splits are made. Terminology that we'll use going forward is that splits on predictors result in subsets or regions of the predictor space, where predictor space generally describes all of the combinations of predictor values. Regions describe particular combinations of these predictors. Before we get to how decision trees make their splits, we need to formalize the idea of node purity. We'll use a measure called the Gini Index for measuring node purity. Let p hat rk denote the proportion of training classes in region R that belong to class K, and let there also be a total of big K total classes. The Gini Index, or Gini impurity measure, is defined as this summation. We sum over all classes these values of proportion times 1 minus proportion. We'll look at some examples in a second, but we can interpret the Gini Index as a measure of a node or region's impurity. It takes a small value when a region is pure, and a region is pure when almost all cases in that region belong to just one class. The Gini Index takes a large value when a region is impure. An impure region has many cases of different classes. Let's look at some numerical examples to understand the Gini Index. The CA variable gives the number of major vessels visible through imaging. Say, for example, that I consider splitting my data based on a threshold of 2 for this variable. I'll end up with 4 cases with heart disease in the right region and 2 of each class in the left region. Just by visual inspection, the right region is more pure than the left region. Using the Gini Index formula, we have that the Gini Index for the left region is 0.5, and it's 0 for the right region. The left region is more impure than the right region. It has a higher Gini Index. This makes sense given that a prediction using the cases in the left region is more uncertain. For a case with less than 2 visible vessels, it's a 50-50 as to whether they have heart disease. On the other hand, for cases with at least 2 visible major vessels, it's entirely certain, at least in the training data, that this individual has heart disease. The goal of using the Gini Index is to guide tree building. We want to use this measure to compare all of the possible splits that could be made. The overall quality of this split, vessels less than 2, can be captured by a weighted average of the impurity of the 2 regions. The weight given to a region is the number of cases in that region divided by the total number of cases in the left and right regions. Here, the overall quality of this split is 0.25. This number isn't super helpful on its own, but our question is, could another split have given us a lower number? We'll see actually yes with this example. If we use a threshold of 1, one heart disease case is moved to the right region. So in the right region, the proportions of heart disease and no heart disease patients are still 1 and 0. So the Gini Index for this region is still 0. But the Gini Index for the left region has gone down from 0.5 to 4/9. This new split has lowered the average Gini Index to 0.167 from 0.25 earlier. So overall, this split gives regions that are more pure, which is preferable in building the tree. Now we can dive into how trees decide on good predictor splits. The algorithm used is called recursive binary splitting, and it proceeds as follows. First, we search through all predictors and their possible split points, and we find the particular predictor and split point that gives us the lowest average Gini Index. This gives us 2 regions, and we repeat this process for each of these 2 new regions. That is, for each of these regions in which a certain subset of the cases is filtered through, we again find the best predictor and split point. This process is repeated over and over to continually split the data into more pure subsets according to the average Gini Index. We stop the splitting once some stopping criterion has been reached. Some examples of stopping criteria are as follows. Stop once all the leaves have less than a certain number of cases, or stop once a region has been split too many times, or stop when there's no possible split that can lower a node's Gini Index. Recursive binary splitting can be described as a top-down greedy approach. The top-down part comes from the fact that we start at the top of the tree with all of the data in one group. And then we split the data into subgroups as we move down the tree. This is in contrast to a bottom-up approach in which each case would start in its own region, and then we would fuse the regions together to build the tree. Recursive binary splitting is also greedy in that at each step of tree building, you make the best split at this particular moment, the one that minimizes the average Gini index right now. But there very well could have been another split that would result in an even better tree in a later step. The reason those lines aren't considered is because many more combinations would have to be explored, which could be too time intensive. In summary, we've learned that decision trees are an interpretable means of performing classification that work by iteratively splitting the data using predictor values. It turns out that trees can also be used to perform regression tasks. This is something we'll explore in class. Trees are built with the recursive binary splitting algorithm, a top-down, greedy approach, which is faster than considering all possible sequences of splits, but this won't necessarily give us the best overall tree. The metric used to judge the quality of a split is the Gini Index, which gives a measure of node impurity, or lack of class homogeneity within a leaf. Finally, you might imagine that there's a great risk of overfitting when we build trees with too many splits. This definitely is a concern. In class, we'll discuss the idea of tree pruning, and we'll explore next extensions of decision trees called bagging and random forests, which can help fight overfitting.